You're listening to the FQXI podcast. Today,
if the previous one was headlined Hawking proved wrong, this one is Einstein proved wrong.
we're counting down the biggest physics stories of 2024.
It's cool either way. Every other nucleus requires gobs more energy. That's just weird. It's a beautiful story. We need to get out of this mentality of more, and we have to get back to this mentality of wonderment. It's a cultural issue, partly, but it's also a money issue.
As chosen by quantum physicist Ian Durham.
Funny side story, when I was a baby, ball lightning apparently formed above my head when I was a child. One of my 3 run-ins with lightning. Okay, so this is number 1 because of the uproar that occurred. So many physicists were taken aback and said, this isn't physics, there's no physics in it at all.
I'm Zia Morali. Welcome to the FQXI podcast. Yes, it's that time of year again when we're looking back at 2024 and the biggest and best stories of physics for our top 5. Of course, I am joined as always by FQXI member and quantum physicist Ian Durham of St. Anselm College in New Hampshire. Hello, Ian.
Hello.
Thank you very much for joining us again.
Thank you for having me. It is a pleasure to be here as always.
We want to dedicate this countdown to a specific person, a friend of yours, who was a long-time listener.
Yes, my friend Carl Gertman, who was a long-time listener. He liked to rag on your pronunciation of certain words, which I kept telling him, well, it's English and she's English, so they're the ones who invented the language, but he didn't like that. But anyway, Carl was a great guy. Carl passed away in September, somewhat suddenly, so I'm dedicating this to Carl, who was a good friend.
I never met Carl, but every time we recorded this podcast, I was very aware of the way that I pronounced the word controversy. Thanks to Carl.
Yes.
And in his honor, I shall continue to pronounce the word controversy as controversy.
Please do.
But I think you should continue to make fun of it on Carl's behalf in his memory.
I will.
I'm thinking that we will have an opportunity for that with this year's list.
Oh, yes.
Not giving too much away, but there will be the use of the word controversy.
Yes.
Or controversy at some point.
Oh, yes, there will be.
Now, we always start with the runners-up, the honourable and dishonourable mentions. We might do something a little bit different this year in that if you're listening to this through your podcatcher or on YouTube, you may hear a shortened version of this list that goes straight in at number 5. But if you want to hear the runners-up, and I have to say, the runners-up could have made, I think a few of these could have made the main list in another year, you're going to have to visit qspace.fqxi.org/podcasts and listen to those, where we covered advances in quantum computing. We covered something sort of mathematical that has relevance to absolutely everything in the universe, including free will. We covered research that solves a huge outstanding mystery that I think we've spoken about on the podcast before in particle physics. And we talked about some evil twins and possibly the most dangerous truck in the universe, or in the world, the most dangerous truck in the world. So go and listen to that if you haven't already, and listen to all of those that very nearly made it.
There's some great ones on this list, some really kind of weird ones on the list too, on the runners-up.
But now,
drum roll please, yes.
Coming in.
Here we are.
At number 5.
Number 5, the world's first nuclear clock is now ticking.
That doesn't sound scary at all, Ian.
So let's talk about clocks. Until, and actually still now, the most accurate clocks these days are atomic clocks, and they've been around for a long time.
So in a regular atomic clock, the clock's ticks are set by the resonant frequency of atoms. Due to quantum mechanics, atoms have discrete energy levels, and as electrons transition between them, they release photons. The current best atomic clocks would take longer than the age of the universe to lose or to gain a second.
The way an atomic clock works is you excite an electron in an atom and it decays. And because of quantum mechanics, the Schrödinger equation predicts that the energy levels are quantized, and it predicts the values that these energy levels will have. And so you can predict very precisely a photon that'll come out of when the electron in the atom settles back down to a lower energy level. It'll emit a photon, and that photon will be very, very, very precise. And in fact, it has a specific energy because of quantum mechanics, and that specific energy is proportional to the wavelength. And so if you know the wavelength, you also know basically an oscillation frequency. It's an oscillating electromagnetic field. So you can use that oscillation, that very regular oscillation, as a clock. That's how an atomic clock works. Atomic clocks are absurdly precise. Why would we need anything more precise than that? And a lot of people don't realize this. But the GPS system, the way it works, is each GPS satellite is essentially a flying atomic clock. And it's syncing the clocks on the satellites up with clocks on the ground. And the syncing of the satellites is what allows you to pinpoint a location. And so they have to sync the clocks using general relativity. So for any listeners out there who think they have proven Einstein wrong and that there's no such thing as special or general relativity. Well, you can believe that all you want, but the equations of general relativity are used, and special relativity, are used every day by people who control the GPS satellites. Right now, GPS is pretty accurate. It's accurate to a few feet. But there are a lot of interesting situations where it would be useful to have it be even more accurate. And actually, I'll give you one from my own life where it would be nice if GPS is a little bit more accurate. So I do a lot of hiking and trekking and climbing mountains. And usually, so I have a watch that keeps track of my elevation. I didn't have the money to buy the expensive watch, so my watch doesn't use GPS. I've got a handheld GPS unit, and even that's only accurate to within 15 feet or something like that.
I'm feeling really sorry for you now, Ian. Listeners, if this tale of woe, where Ian doesn't even have, a really fancy smartwatch, is tugging at your heart, and you would like to help Ian buy a more fancy watch, you can head to keyspace.fqxi.org/podcasts. And there I will have a link for making donations to FQXI's fund for Ian's new smartwatch. Yeah, all right. I'm joking. But we do take donations to fund science outreach and research, not watches. You probably could donate for Ian to research free will, which if you listen to the bonus material at keyspace.fqxi.org/podcasts, you will know that he works on. So please do consider giving us a donation, although possibly not for a watch.
I should add, I also, in addition to doing free will, I do work on time. And in fact, the last month that I was in Madison, in addition to doing sort of causal emergence stuff, we were actually directly addressing the issue of time.
Oh, well, that's perfect. You could send some money in to fuel Ian with tea and biscuits or coffee and donuts while he works on time.
Yes.
Just put in a little note, send us a message at podcast@fqxi.org to say that you've given, a $5 donation just for Ian.
Why, thank you.
So that the money goes to the right place.
Yes.
One important application that you haven't mentioned, and I do want to note, is that more accurate clocks would help to improve GPS location accuracy enough to be useful to help blind people or people who are visually impaired, which I do think is hugely important.
Oh, I actually did not know that. That's interesting.
Yeah, and also...
Yeah, that's great.
Autonomous vehicles are mentioned too.
A perfect example of this is self-driving cars, which I'm not a big fan of, but nevertheless, they exist. And if you want them to be accurate, you have to get your GPS really down to inches. Deep space navigation, we'd like something better. So to escape the clock-contaminating noise, they've been trying to sort of zoom in past the electron shell and try to work with a similar principle at the nuclear level. So just as electrons get excited and drop down and then emit very precise photons. So do nucleons, like protons and neutrons inside a nucleus. And that's what they have done. And it's, in fact, the same group that runs the timekeeping here in the U.S., NIST out in Boulder, Colorado. And they've now got a working nuclear clock.
Before we get into how the clock works, why it's so good, I should also say that last year we started a new tradition. I don't know if you remember this, Ian. We offered to give away FQXI merchandise, FQXI t-shirts.
Yes, we did.
To any of our winners who were listening and contacted us and asked for it. We did get one request.
We did. Oh my God.
Not just a t-shirt, but he was a little bit cheeky. I think he actually got a hoodie.
I think that's awesome. That is so cool.
And those hoodies, let me tell you, are very comfortable. They're really nice. So what you could do if you're listening and you are a really sneaky, unethical person is you could go to our website, go to our shop, buy yourself a t-shirt, a hoodie, a bag, a hat, and then just go around telling people that you were on Ian's list.
You could do that.
If you are a winner and you listen to this, you can contact us and you can claim a t-shirt. I think we will limit it to one t-shirt per winning team, just in case, the LHC is one of the winners, because we would be bankrupted if, everybody at the LHC came in and asked for merchandise. But there will be one exception where I think multiple people should be allowed to claim t-shirts.
We could become as popular as the Nobel Prize.
I don't think the Nobel Prize even gives out t-shirts.
I don't think they do, no.
Try and think back to your last Nobel Prize, Ian.
Yeah, my last one, I can't remember what they gave me.
But let's talk about this clock. And I think guys from this group also work on all sorts of different clocks. And they worked on the optical lattice clock, maybe that we spoke about before, and put some links up.
There may be some overlap, yeah, because it's a big group out there in Boulder. And there were also some people from overseas, Max Planck.
So there's a nice article that I'm looking at from Scientific American about this, where they explain that if an atom were the size of an American football stadium, so I have no idea how big an American football stadium is myself, but Americans will know, and the rest of us can imagine, very big.
It's big.
The nucleus would be only as big as a marble. And then they go on to explain, and I think Ian you're going to tell us more about that, what it is about trying to kind of trigger these transitions with the nucleus, why that would create a clock that has less drift.
Yeah, so first, in regards to the American football stadium, so an American football field is roughly the same size as a rugby pitch. In fact, American football grew out of rugby, so it actually has about the same thing. And the stadiums in the U.S. seat like 70 to 100,000 people. So now, the thing is exciting a nucleus. So first of all, exciting something so tiny requires remarkably, so not only just exact and very coherent laser, so you do it with a laser, but it would require usually thousands or millions of electron volts of energy that are precisely tuned to very specific frequencies. And to excite an electron in an atom, you don't have to be quite as exact, in the sense that there's a little bit of buffer room. It's fairly easy to excite atoms. I mean, anytime you have anything glow in the dark stuff, a t-shirt or whatever. But a nucleus is so tiny, in order to get in there and to really excite it, you have to be so exact that because of the exactness, you are going to have less drift. That's kind of why a nuclear clock will drift a little bit less, which means it would tick more times per second. So another way to put it is the energies are so much higher. Higher energy means shorter wavelength, which means faster ticking.
So why hasn't a nuclear clock been built before?
The problem is that most tabletop lasers just can't generate enough energy to excite any nucleus because the energies are so stupidly high. But there is one strange exception, and that is a rare radioactive isotope of thorium, thorium-229. And that isotope, for some bizarre reason, only requires about 8 electron volts of energy to jump to an excited state. And 8 electron volts is very little. Like, that's very little energy. I'm not sure anybody understands why it's so low, but anyway, it makes it really useful. It's a golden opportunity here for building a nuclear clock.
So this study, we'll put a link to it. It's published in Nature, and we'll put a link to it on qspace.fqxi.org/podcasts. One of the authors, Torsten Schum, has said in this article in Scientific American that this could be useful for revealing something about dark matter.
Yeah, so I read that too, and I have no idea. I will leave that for the dark matter experts.
Yeah, I mean, I guess he's claiming that because dark matter doesn't really interact with anything normal around us, so we can't really detect it successfully. But maybe there is a possibility that dark matter could interact with the nucleus differently than it would with a whole atom. And so maybe, I guess if you do an experiment with a nuclear clock versus an atomic clock, maybe you might see a difference in the results.
Maybe.
Who knows?
Who knows? I mean, I think that's great. It's an interesting conjecture, but I have my doubts about that. Maybe I'm just in a grumpy mood.
There seems to be a theme where these articles end on an intriguing but perplexing note. I think we've had another one of them in the bonus material.
It's cool either way. I think it's cool either way. From a foundational standpoint, it's really important because why does thorium-229 only require 8 electron volts to excite, whereas every other nucleus requires gobs more energy? Like, that's just weird. Because the only difference between, say, thorium-229 and thorium-228 or thorium-230 is a single neutron. That's the only difference. And why does a single neutron suddenly change the binding energy so dramatically? Like, that's odd. Now, that being said, also from the clock standpoint, time, understanding how accurate we could be in time tells us a lot of things about the nature of time and also space, because I would imagine if you had a series of clocks on satellites, they would be much more sensitive to, for instance, curvature in space-time. It also could be useful in improving, gravitational wave experiments. The timing between the satellites is a way of detecting gravitational waves. So, there you go.
So if you are one of the authors of this paper, then get in touch with us for your t-shirt and also tell us about some of these exciting things that could be explored and whether dark matter really is one of them, and if so, how. And we'll of course have more details about this work on the podcast page, qspace.fqxi.org/podcasts, and I will also link to an interview about optical lattice clocks. We're going to move on to number 4.
Yes.
And I did tease at the beginning that there would be one item on the list where I think more than one person on the team should be entitled to a t-shirt. I think all the people on this team who came up with this result are entitled to a t-shirt if they would like to contact us. But
yes,
as you explain it, I think people will understand why.
I would love to see, I hope that word maybe gets out to these guys about this award. So there was this great result in mathematics that came out this year from 3 high schoolers in Canada and their mentor. They were looking at a problem that goes back 100 years that relates the idea of a knot, like tying a knot, to this concept of a Menger sponge. And a Menger sponge, perhaps you've seen it, you start with a solid cube. You think of it like a Rubik's Cube. And then you remove like the middle cube on each side. And then for all the remaining cubes, you do the same thing. You divide each of the remaining cubes up into cubes, and you remove the middle cube. And then you divide each of the remaining cubes of those cubes into cubes, and you remove the remaining cubes. It's a fractal-like thing.
And we'll put links on qspace.fqxi.org/podcasts as well to pictures where you can see this. And can you just explain how is the Menger sponge connected to knots?
So knots, or they're something that you study in topology. And topology is a branch of mathematics that studies essentially topological things. So like topographic maps, if you know what topographic maps are, right? The spatial dimensions of things. One of the famous things of topology is that a coffee mug is topologically equivalent to a donut. right? Because they both have one hole. If a coffee mug were malleable, you could move it into the shape of a donut without actually, changing the fact that there was a hole in it. So in topology, this idea of knots is that every knot is somewhat equivalent. So when I say somewhat equivalent, the mathematical term is homeomorphic to a circle. Okay? And Menger, and this was 1926, so it was actually 98 years ago, when he first devised his sponge in 1926, he proved that any conceivable curve, anything from simple lines and circles to all sorts of things, trees, fractal dust, whatever, can be deformed and then embedded somewhere in his Menger sponge. Basically, they can be made to wind their way along the sponge's contours without ever leaving its surface. Okay, so now if you look at a Menger sponge, what's interesting is when you start to try to define what the surface is, because you're taking pieces out, and so that you're left with almost nothing, even though you're left with like an infinite amount of things. It's a little strange.
We've got here, I'm looking at this article from Quanta, and they say, after infinitely many iterations, the shape's volume dwindles to zero while its surface area grows infinitely large.
Which is just weird, but infinities are like that. Infinities are wild and cool. But anyway, Menger's statement didn't actually distinguish between homeomorphic curves. So his proof only guaranteed, for example, that a circle could be found in his sponge, but not that all homeomorphic knots could be. Meaning, you can always take a knot and ultimately it's homeomorphic to a circle, but could you then embed the knot in there and still have all its tangles intact? So if you tie a knot in something, can you keep the shape of the knot intact, meaning all the little tangles? Well, this passes this way through this thing and around there. Could you keep that intact and still have it in the Menger sponge? And here's the interesting story. So this guy, Malors Espinosa, was thinking about this problem, and he also ran this program for high school students. It was a summer enrichment program for high school students. He had 3 students, and he had been teaching them about basic ideas in math research, showing them how to write proofs. But there were a couple of students who wanted to do more. They really wanted to do what it means to do math when there's no answer key kind of thing, right? And so he was looking for a problem that they could really approach. And that's when he came across this problem. And so he had weekly Zoom meetings with these 3 high school students, Joshua Broden, Noah Nazareth, and Nico Voth. And after just a few months of weekly Zoom meetings, they were actually able to show that all knots can indeed be found inside the Menger sponge. In fact, they actually found that the same could be said of another related fractal as well. I just think that is just so cool. I mean, they were high school students. They were very talented, smart high school students, but they were, they're still just high school students.
I have to pull out a quote from this article in Quanta, which describes the situation where the students started to struggle when they thought they had a promising avenue of attack. And the quote from their mentor is, "We're facing math, and math has no mercy."
Yeah. Yep.
I know lots of mathematicians who I think would be nodding their head when they hear that math has no mercy.
Yes.
Let me ask you, Ian, is this number 4 on the list because of the actual problem that has been solved, or is it because it was students, it was very young people who solved it at school?
Well, it's on the list because of the problem, because this is a 98-year-old problem that has been solved. That's pretty amazing, and it was solved in a very clever way. If you look for the paper or you go to like the Quanta magazine article, you'll see how they went about translating the knots onto a grid-like structure, which is what the Menger sponge is. And so you'll see the basic idea of what they were doing. What I like about it, if anybody out there has ever actually read a paper on topology, so when you look at topology in the news, and they always have these great, cool pictures of fractals and lots of great pictures, right? It lends itself to great pictures. But the papers are dense mathematical proofs, and there's always lemmas and theorems and propositions, and they're not often a lot of cool pictures. What makes this problem intriguing is the students didn't necessarily need to have that jargon, that language, in order to get started with it, because they had come up with this idea of doing this mapping of knots to grids. It's just this great visual thing, and it's a way of showing that sometimes less is more.
This was Canada.
Indeed it was. This was in Canada.
This sort of thing I don't think would, well, maybe it does, but it's very rare to happen in the UK. I imagine it's rare to happen in Canada or anywhere in the world. Is there a way to make it less rare? Perhaps not in the sense that teenagers are getting these fantastic results that make it to international news and to FQXI's list, but just to get students exposed to, as this article says, the pain of math research, that math has no mercy, or that physics has no mercy, or actually the joy in doing this kind of research.
Yeah, I think there is, but I think the answer is, as it always is, there needs to be money for this kind of thing. I think there are enough mathematicians and physicists and computer scientists out there who would be interested in taking some of these things on and doing this kind of thing, but in order to do it, they need to be paid for their time. The reason is because so much of our lives these days, as physicists, mathematicians, computer scientists, whatever, is taken up with grunt work. So there's a lot of our job that is not science. It's grant reports and all sorts of other stuff that has to be done that's administrative. And in order to get out of doing that, you have to pay somebody. So if the university is not getting your services, they're not going to pay you. And so you have to make up for that by getting paid. So there has to be some money for it, and there has to be some money for the students.
I should say that FQXI's Fulcrum Grants Programme, the programme formerly known as the Mini Grants Programme, does give money towards a huge range of projects, including outreach to high school students. Some cost only a few $1,000s. While you're visiting QSpace to listen to the bonus material, take a look around the main site. The main site is fqxi.org to learn about some of the outreach projects that FQXI has supported in the past. I'll be adding information to the podcast page, qspace.fqxi.org/podcasts, about how to donate to FQXI. And if you would like to help to support science and maths outreach for high school students specifically, then by all means send a note with your donation to podcast@fqxi.org specifying that. For these kinds of projects, even small donations can very quickly add up and have helped FQXI's physicists create quantum computing workshops for schools and to run summer programs at a dark matter laboratory in Italy, just to name a couple of things, for instance.
There has to be a sense that it's worth doing. And so much of things now, it's all about, my summer internship, I've got to come out with this measurable result. Because, incidentally, for students right now going to grad school, now these students are high school going into college, but going to grad school, in the U.S., you now have to have 3 or 4 publications. Get into grad school as an undergraduate, which is crazy.
Yeah.
It's crazy. And, what's going to happen to the high schoolers? Are they going to require publications now? I think that's insane. And so the research opportunities are becoming extraordinarily competitive. And there has to be a way to either make them less competitive. The only way I can think of how to do that is to fund more of it so that you have more. I'm not big on that. I don't think you should be publishing. Maybe as an undergrad you should have one paper, maybe. But I didn't. Did you?
No.
As an undergrad? That's kind of crazy. I think we need to get out of this mentality of more. And we have to get back to this mentality of wonderment. It's a cultural issue, partly, but, it's also a money issue.
This has taken a sad turn.
Yeah.
It seemed like it, and it is. It's a beautiful story.
It's a beautiful story.
About the achievement by the students. But yeah, it feels like we've moved into a discussion of something that's been plaguing academics in terms of having to publish, and now that's kind of seeped lower and lower down into high school, or into at least the undergraduate level, and maybe potentially to high school. Let's hope we don't end up going in that direction. In the meantime, very well done to the 3 students here, all of whom I'm pleased to say are considering going into a career in mathematics.
Yes.
I do feel bad that I had to say math when I was quoting directly.
Because it's maths.
From North Americans, yes. But maybe Carl would have been happy with that because I didn't say maths.
Yes, he would have been happy with that.
There we go. So that was number 4. Shall we move on to number 3?
Yes, number 3. When I sent this to you, my heading was Hawking Proved Wrong. Stephen Hawking had this idea about black holes.
A black hole, of course, is thought to be created when a huge mass collapses into a very tiny region or singularity at the black hole's core. It's shrouded by an event horizon, and the idea is that the pull of the black hole's gravity is so strong that anything, including light that passes this surface or event horizon, will be pulled in inexorably. They were predicted by classical physics, but Hawking and others since have examined quantum effects related to these entities.
There are these sort of edge cases with black holes, and as matter falls into them, they tend to spin faster and faster and faster. And if that matter has charge, they also become electrically charged, which also gives them a magnetic field. And in fact, side note, the magnetic field of the black hole that the Event Horizon Telescope has seen has been mapped, so you can actually see the magnetic field. But anyway, at a certain point, in theory, a black hole can reach a point where it has about as much charge or spin as it possibly can, given what its mass is. That's called an extremal black hole. And they have some strange properties. For instance, at the event horizon, the surface gravity is 0, which is just bizarre, right? The whole idea of a black hole is that it's supposed to be completely, way more extreme than that. So it's literally a black hole whose surface doesn't actually attract anything. But if you nudged a particle slightly to the center, it would be unable to escape. But in 1973, Hawking, along with James Bardeen, who I think is the same James Bardeen who won 2 Nobel Prizes. Isn't that the same Bardeen?
Yeah, there's a James Bardeen who worked on black hole thermodynamics, and then there is his father, John, who won 2 Nobel Prizes in physics for inventing the transistor and for being the B in the BCS theory of superconductivity.
Oh, that's right. One of the Bardeens is one of the few people who have, actually the only person to have won 2 Nobel Prizes in physics. But in any case, it was Hawking, James Bardeen, and Brandon Carter basically said in 1973 that extremal black holes can't exist in the real world. There was no plausible way that they could form. But, they've been studied nevertheless for the past 50 years because they have nice symmetries and things. And there are a couple of mathematicians. It's Christoph Keel, of MIT, and Ryan Unger of Stanford and Berkeley, basically have shown that there's nothing in the known laws of physics to prevent the formation of an extremal black hole.
Why did we think that we couldn't form one, if they've shown that there's nothing to prevent one being formed?
Well, I think that's a good question. Maybe because Stephen Hawking of all people, asserted it to be true, that they couldn't form. Their assertion was based on sort of
vibes.
Yeah, well, more than vibes. Kind of, it was based on arguments of practicality in a way. General relativity allows for wormholes, which raises a whole bunch of time travel paradoxes. And so this is allowed by the math. We don't see them, of course. How do we say, why do we not see it in the real world? And how do we know that it's never going to happen in the real world? Well, we have these assertions, like the universe must be self-consistent, for example, that kind of thing. So I think that's why we have long just assumed they couldn't exist, even though there's nothing in the laws of physics that prevent them from existing.
And it looks like one worry that people had was about the possible production of naked singularities.
Yeah.
In the way that it's described that these extremal black holes would form, it's from sort of a dense cloud of charged matter that collapses to form an extremal black hole. And then the worry was if you put a bit more onto it, then it might collapse into a naked singularity. So that's like the core of a black hole, but without being shrouded by an event horizon. And I guess that brings in some of the sort of time travel quandaries and all sorts of weirdness that could be allowed if singularities were wandering about the universe without any kind of event horizon sort of protecting us from them. But they have shown that this actually wouldn't happen, because if you did add more charge to this cloud of matter, it actually would somehow disperse rather than forming a naked singularity. There'd just be no black hole at all.
Right. I should mention, by the way, that the argument by Hawking, Bardeen, and Carter is they were studying black hole thermodynamics at the time. And they were talking about possibly 4 laws of black hole thermodynamics that are supposed to be consistent with the laws of statistical mechanics and thermodynamics. And it was the 3rd law, which is like its standard thermodynamics counterpart, that they couldn't prove exactly, and so they just kind of asserted that, well, the others are correct, the 0th, the 1st, and the 2nd. The 3rd just must be there.
A simplified way of stating the 3rd law of thermodynamics is that you can't cool a system to absolute 0 in a finite time or with finite steps. And the equivalent for black hole thermodynamics would prevent a black hole being created with 0 surface gravity in a finite amount of time.
That's another way of saying there's no way to create an extremal black hole. And so they were just asserting that this 3rd law must be true. It must exist. This raises an interesting issue about thermodynamics and statistical mechanics. There are things that exist out there that we know are true that it's hard to get a true mathematical explanation of. Like the 2nd law of thermodynamics, which says that for any closed system, the entropy always increases or stays the same, on average. It's not a theoretically derivable result. That's an empirically observed phenomenon. So similarly in this black hole thermodynamics situation, sort of this analogous thing of what's going on at the black hole level, the 3rd law, they were assuming they could find it eventually, that maybe there's a mathematical way to derive it. But it may be true that that just is not the case, and that, in fact, the law just doesn't exist. And, in fact, that's what these guys seem to have shown. It's tricky. You get into this situation where you're talking about proofs, but then you also run up against physical laws, and some physical laws are not necessarily because of mathematical things, right? And so there's always this tension between the math and the physics a little bit.
Given that we've called into question this 3rd law of black hole thermodynamics, does that mean that, by analogy, we now have to call into question the equivalent law of classical thermodynamics?
No. So there's a correspondence here between the black hole thermodynamics and regular thermodynamics, but that's a correspondence. It's a little murky about the relationship. I mean, we know that there is a relationship between, say, the black hole's surface size and its temperature and stuff like that. It's another Hawking result. In fact, some of this stuff, I think, was even done with George Ellis, FQXI member, because back when he worked with Hawking in the 70s. Here's the thing. I'm going to quote Feynman, paraphrase that, if your results are not consistent with experiment, they're just wrong. It's all about experiment. And what do we see in the world? I mean, that's what science is about.
This also sort of harks back to one of the runners-up, where theory came into conflict with experiment, and maybe experiment might have won.
Yeah, correct.
One more question before we move on.
Mm-hmm.
So this result tells us that these extremal black holes could exist. Do they exist? Oh, you can't answer that.
I can. Yeah.
But is there a way that we could observe if they exist? Because you spoke about the Event Horizon Telescope giving us a beautiful picture of a black hole event horizon. And, there are ways of indirectly inferring that black holes are here, there, and everywhere. But is there a way that we could say, okay, this one's getting right to the edge. This one could be an extremal black hole, or is there just no way of?
That's a good question. I don't know off the top of my head, and I'm not clever enough to necessarily say yes or no, other than to say that I wouldn't rule it out in the sense of, do they exist? It's very possible that they simply don't exist. Even though it's possible, even though this result proves that it's possible for them to exist, it's very possible also that they just simply don't exist, that there just are none in the universe. Putting that aside, I could imagine that better telescopes might be able to get better and better and better. I mean, first of all, there's no surface gravity at the event horizon, so there would be some strange behavior right at the event horizon. So if we had the ability to focus in on one really right down to the nitty-gritty there at the event horizon, we might see some signal. Whether they actually do exist or not, that's also another question.
Links, of course, to this extremal black hole paper and more can be found on the podcast page qspace.fqxi.org/podcasts. Right, so that was number 3 on the list. Let's turn to number 2.
Okay, so if the previous one was headlined Hawking proved wrong, this one is Einstein proved wrong.
I don't know if you're aware of this, but when you were talking about, was it the nuclear clock?
Mm-hmm.
You made a comment about people who claim that Einstein has been proved wrong.
That's wrong, yes, right.
And said they were crazy because of GPS. And now you're going to eat your words.
And not only am I going to eat my hat, I actually know the people who did this. Eduardo Martinez. So there's a thing called a Kugelblitz. I love that name.
That is the best word. It's so cute. Kugelblitz.
Kugelblitz. And a Kugelblitz is literally a black hole formed by purely light. What's the idea? Well, the idea is that in relativity theory, matter can be converted to energy and vice versa. E equals mc squared. So you could imagine that you could have a black hole that's, instead of made out of solid matter, is actually made out of just energy, which would be electromagnetic energy. Such a thing would be called a Kugelblitz. But actually producing a Kugelblitz appears to not be possible, and that is due to this work by Eduardo and his colleagues. Eduardo's at the University of Waterloo in Canada. They have a paper in PRL, Physical Review Letters, that says, no known source in the current universe would be able to produce it, neither artificial nor natural. I guess Kugelblitz in German means ball lightning. Funny side story that I'll just briefly mention. When I was a baby, ball lightning apparently formed above my head when I was a child.
Oh my goodness.
Yes. When I was a baby and in high chair, and I had a metal high chair, and after that my mother got rid of the metal high chair.
Wow.
Got a wooden one, yes. One of my 3 run-ins with lightning.
What is going on? Okay, we have to talk about your run-ins with lightning now.
Oh, yeah, so I've nearly been struck by lightning 3 times. That was time number 1. Time number 2, I was in an apartment in Boston when I was a kid, and the windows were open.
You were indoors and you nearly got struck by lightning.
Yes. Oh, I was indoors the first time. I was in my kitchen.
Yeah, ball lightning's weird though.
Yeah, ball lightning's very strange.
Yeah.
For a long time, people thought it was crazy and there's no such thing, but now they're pretty sure that it's a real thing. Although that one video online that claims to show ball lightning on the railroad tracks is fake.
Right.
Just so you know.
Okay.
And then I was at a concert in 1999 in D.C., and it hit a woman 20 feet from me.
Oh, so. My goodness. What happened to her?
She was okay. She was burned very badly. She had 3rd-degree burns on her leg, but she did live.
Wow.
But anyway, so Kugelblitz means ball lightning in German. And apparently there's a Kugelblitz in season 3 of a Netflix show called Umbrella Academy that obliterates large swaths of existence, which I never heard of Umbrella Academy.
Now, don't go spoiling people who haven't seen the 3rd season of Umbrella Academy. I haven't seen any seasons of it, but...
Oh, yes, I don't know.
You know, there might be someone who's just finished season 2 and now is like, I'm never listening to this podcast again.
Well, yes. Well, I didn't tell you what it obliterated, but anyway. So what Eduardo and his colleagues have shown is that forming a Kugelblitz in a laboratory would require light intensities more than 10 to the 50 times that of standard laser pulses, which is a mind-bogglingly large factor. It's a 1 with 50 zeros after it. And in nature, the brightest quasars, which are some of the brightest things in our universe, they're these luminous centers of active galaxies, are way too dim. They don't even come close to that. It's in fact, this kibosh on Kugelblitzes, as one of the stories quoted, it rules out itty-bitty Kugelblitzes even as small as 1/100th of a quintillionth of a nanometer because of, again, the amount of energy that it would require. So there apparently are never going to be Kugelblitzes in the universe. This is very sad.
Oh, that is sad. Well, probably good for you because they'd probably head straight for you for some reason.
I know, they would just, yes, they would be coming for me.
Coming in that dangerous truck.
Yes.
Autonomously driven, helped by the ultra precise locating GPS from the nuclear clocks.
Yes, indeed.
There is a loophole, however. Having said that they might not form, these tiny little Kugelblitzes, under their own gravity, there is a loophole that they might have happened just after the Big Bang.
That is true, but a lot of things might have happened after the Big Bang. It is entirely possible that right after the Big Bang, there might have been enough energy, because I talked about how much energy you needed to have, 10 to the 50 times that of a standard laser. But inflation, which happens early on, and if you want to know more about inflation, you can read Zia's book.
Thank you, Ian. You've mentioned my book, A Big Bang in a Little Room, on the bonus material without any prompting. So thank you for that, and thank you for doing it again. Links to the book are on the podcast page. And the book does discuss how the early universe went through a rapid growth spurt of inflation.
Yes.
In quite a lot of detail.
Cosmic inflation may have even left signatures, sort of fluctuations of the curvature of space-time that might have caused light to collapse into some kind of what's known as a primordial black hole. In other words, light can't form a black hole by itself. However, after the Big Bang, it's possible that inflation could have caused some primordial black holes to exist.
I wrote an article quite a few years ago, and it was a little bit tongue-in-cheek, but it was based on a paper that suggested that primordial black holes are flying through Earth and causing our computers to glitch. When your computer glitches, it's a primordial black hole.
I have heard that.
Your computer probably glitches more than other people's. Like, that would be a way to know if it was happening because the primordial black holes are attracted to you.
That's very possible. That might explain a lot about me, in fact.
So, throughout this episode, listeners may have noticed and been rather annoyed by the fact that I keep plugging FQXI's donation page in case, you want to give money for Ian to buy a smartwatch. Not really. Or more seriously, to research free will or the nature of time and so on. But now I think that maybe we should be creating a fund that people can donate to put towards research into why Ian Durham keeps attracting lightning.
Yes.
But also on the podcast page, of course, we will have links to more about Kugelblitzes, qspace.fqxi.org/podcasts. Those last two stories on black holes seemed really rather cute, Ian. Maybe you were in the mood for something sweet before we get to number one.
All right.
So, listeners, get yourself a cup of tea or a cup of coffee and sit yourself down if you're doing something else, because this could get bumpy.
Yes. So, the winners of this year's award...
FQXI, the FQXI award, Ian.
FQXI award, yes.
Yes.
So, I want to just preface this by saying that every once in a while, one of my top fives is less a discovery that happened in that year and more of a news story that happened in that year. And this year's number one is the Nobel Prize in Physics that was awarded this year to Geoffrey Hinton and John Hopfield. There's a lot of controversy or controversy about this award. The first bit is because Hopfield and Hinton were awarded the Nobel Prize in Physics for essentially artificial neural networks, which a lot of people kind of scratched their heads and said, is that really physics?
When you say scratched their heads, if you were on Twitter that day, or that week, or that month, it was like devastation.
Yes.
I mean, it was like some kind of tragedy had happened. Physicists were just crying. They went into mourning. There was like proper grief. There were, just discussions of whether this was the end of physics and, what kind of terrible, terrible thing had happened here. I'm just trying to paint a picture for our listeners of the comments that were out there. And I'm interested to see whether, Ian, you also reacted that way or not.
Well, so as someone who works in a lot of really different areas, part of me has the attitude that everything's physics. Physicists are notorious for crashing other people's parties. So if the award is going to physicists, John Hopfield is a physicist. Geoffrey Hinton is technically a computer scientist and cognitive scientist and cognitive psychologist. And physicists work in a lot of different areas and make a lot of contributions to a lot of different things.
I should add that FQXI member and quantum physicist Gerardo Adesso argued on QSpace, on our site, that AI research is physics, and I will add a link to his post in reaction to the Nobel Prize announcement on the podcast page, qspace.fqxi.org/podcasts. But Ian, in your view, is AI research itself physics, as opposed to being research that was done by physicists?
Well, everything's physics. Physics is the fundamental science. Everything in the universe has to obey the laws of physics. So you could argue that anything is physics. I mean, physicists have invaded Wall Street even. But, neural networks are used a lot and studied a lot in physics. And there's a lot of applications in computing and quantum computing, which is all driven by physics. For instance, Hopfield networks, which are named after John Hopfield, I've come across them in my work before. So I should say it's related to the notion of machine learning and computer science. So machine learning is what really powers the AI revolution. I think some of the criticisms of this award were because of the fact that I think people thought that the Nobel Committee was jumping on the AI bandwagon by giving this out.
It's worth noting that the Chemistry Nobel Prize also went to Demis Hassabis and John Jumper of Google DeepMind for using AI to better understand protein folding. And that also ruffled a few feathers.
Yes. I will say that I am agnostic on whether this is truly physics or not. I don't want to weigh in on that debate per se, but it is a huge debate.
We should talk about what it is they actually won for, though.
Yes, I think we should start there, because then people can kind of make up their own minds. So what they were awarded the Nobel Prize in Physics for is basically the development of artificial neural networks. It's basically a model that's sort of inspired by the network of neurons in the human brain. Basically, they're nodes that are connected by connections, and the neurons are either on or off. And artificial neural networks, they're connected in a graph-like way. So each node in the graph is a neuron or an artificial neuron, and it's connected to some other nodes prescribed by the model you're using. The connections can be one way or they can be two ways, so it can be a directed graph. There's lots of ways of connecting them up, and then there are rules for updating the network. So you have a network that's at a given state, and so each of the neurons is either activated or not activated, and then you update the state to the next state, and the state changes. Some of the neurons turn off, some turn on, and there's an updating rule for how the neural network evolves. And you can train them because it turns out they can learn from experience, in a sense. I don't want to say this to suggest that they're necessarily sentient. This is the way the algorithm works. The algorithm takes in information that is then used to update how the process goes to the next state. And so it's constantly updating and learning from previous states. And that's where the machine learning part comes in. That's artificial neural networks in a nutshell.
Can you talk a little bit about where this touches on physics specifically? Because some of their research is related to concepts directly in physics.
So Hopfield is particularly known. So he is a physicist. In fact, he was a graduate of a liberal arts college. He went to Swarthmore. He worked in Bell Labs for a while. So he was doing properties on semiconductors. And then he worked on a quantitative model to describe cooperative behavior of hemoglobin. Classic physicist, right? This is a physicist who's really dabbling in things. He worked with Linus Pauling, another double Nobel Prize winner. Pauling won both the chemistry prize and the Peace Prize. And eventually he worked on the interaction of excitons and crystals, and he coined the term polariton, quasi-particle that appears in solid-state physics. When you're starting to deal with crystals and stuff, right, you're dealing with lattices. So you're now starting to deal with like a networky kind of thing. It was in 1982 that he published a paper called Neural Networks and Physical Systems with Emergent Collective Computational Abilities, where he introduced this idea of a Hopfield network, which is an artificial neural network that can actually serve as a content addressable memory, the type of computer memory that is used in really high-speed searching applications. And it speeds up the routing of information around a network so it can enhance the machine learning capabilities of a system. And then Geoffrey Hinton was a computer scientist and a cognitive scientist and psychologist. Hinton has been referred to by many as the godfather of AI. He co-invented in 1985 something called a Boltzmann machine, which is what's called a spin glass model, which is a stochastic icing model, which is, again, a statistical mechanics thing, and it is, again, a network kind of thing. What I'm trying to do is emphasize that there is like legit physics here. If you're interested in where the physics comes in, look up Boltzmann machines. He's made a number of contributions to the neural network research, including time-delayed neural networks, Helmholtz machines, and a few other things. They didn't cite one specific thing for Hinton. The key is that, again, he's developing sort of concepts from physics to prove machine learning. You know, whether it was done with that intention or not, I don't know. So that's what Hinton and Hopfield won for.
We don't always include the Nobel Prizes on our end-of-year list.
No, we don't.
They rarely get to number one, or sometimes they get to number one, I'm not sure. This one has got to number one. Why?
Well, okay, so this is number one because of the uproar that occurred. So many physicists were taken aback and said, this isn't physics. You know, they're jumping on the AI hype bandwagon. There's no physics in it at all. And that certainly was an interesting point. So noted. I would also like to note that they have also been, strangely enough, accused of plagiarism by someone who was actually cited by the Nobel Committee when they do the Nobel citation. They cited work by another AI pioneer who has accused them of plagiarism not against himself, but against people in Ukraine and Japan in the 60s and 70s.
Yeah, we want to be very clear. These are all just allegations that have not been investigated and may well not be founded, that have been made on social media by one person.
Yeah.
FQXI has not specifically looked into them. And as far as we know, there have been no official claims of wrongdoing. I think we're simply bringing this up because it's just very curious that a Nobel Prize in Physics announcement should generate so much negativity and so much controversy online.
Yeah, they're allegations, and I'm not saying he's right or wrong. I just, it's unusual, and I don't know what to make of it because he's not a crank. He was literally cited by the Nobel Foundation in the scientific background to the 2024 prize. So he's one of the people who didn't get the prize but was mentioned by the prize. I haven't gone back and looked at the paper's claims. It's interesting from a sociological standpoint that this is why did this award suddenly stir up so much controversy? I don't know Hinton and Hopfield at all, but I mean, they've done good work. These are really good scientists in terms of the work that they've produced. So I don't know anything about them personally. They have a good body of work for their careers on really pushing the boundaries on some of the things that they've been doing. Really good stuff.
I can't claim to know either of the Nobel laureates well, but I should say I have interviewed Geoffrey Hinton in the past for Nature Research a few years ago when he won some other award. And for what it's worth, he seemed like not only a brilliant scientist, but also a very friendly person who was extremely generous with his time and spent a few hours talking to me and really taking me in great detail through his breakthroughs. This was all over the phone, but he was writing equations on a blackboard while he was speaking to me. I couldn't see it because it was audio, but he was sort of speaking them out to me as he went along. He went into a lot more detail than needed for the article, simply because I was just curious about how he had come up with some of his breakthroughs. And I just wanted to know how he had developed these ideas. And he was just kind of talking me through that. And he was really excited that I could understand the mathematics behind it. And so he was kind of walking me through that. It's perhaps not the most thrilling anecdote. Nobody got struck by lightning. But just to say that, he seemed like a really nice guy.
And I should also point out that the only equivalent award in the computer science community is the Turing Award. So there's no Nobel Prize in computer science. But these guys are working in such interdisciplinary areas, where would you give them a prize? So they gave them the physics prize, and a lot of people were rubbed wrong like that. But if you wanted to give them a prize, what prize would you give them? And then it's complicated by the fact that then there are these accusations about what they're doing, their work is not original.
On the topic of plagiarism in general, and here, I think the word plagiarism often conjures up images of people deliberately taking and copying other people's work. But perhaps more of what the complaint is here, and very often, is that there's a lack of citation.
Yeah.
And the person making the accusations really seems to be talking about a lack of citation etiquette in terms of referencing the work of other people that have been done before once you become aware of it, assuming you have become aware of it.
Yes, one of the points that is argued is that the Boltzmann machine paper that Hinton co-authored in 1985 apparently didn't cite the first working algorithm for deep learning of what's called internal representations by these Ukrainian guys from 1965. Now, I'm a proud Ukrainian American. However, I also had the experience of back in the 90s working in aerospace industry right after the Cold War ended, and it was very interesting to see that there were all these discoveries that the Russians and the Ukrainians and the Soviets made in various fields during the Cold War that no one ever learned about because they kept them under wraps or something. There wasn't a lot of communication between the Soviets and the West. It's plausible to me that the Ukrainians published in a journal that no Western scientists would have read until the 90s or later. I just remember going to these conferences. Someone would present a result, and then at the end, some Soviet guy would raise their hand and say, yeah, we did that 30 years ago. And frequently they did. And it just never came out because, it was classified or something like that. I don't know. I don't know about this. I'm not sure about the Japanese work. It is possible for people to independently come up with ideas. And it's also what seems like an accusation of a lack of citation versus plagiarism. Like, I'm not so sure I'd use the word plagiarism. Nevertheless, again, I would dismiss it out of hand if it weren't for who it came from.
Because you reminded me of my book, which I had forgotten I had written, and also the name of, but you were talking about papers coming out of the former Soviet Union and also Japan, and it just reminds me that there are whole sort of stories about the work that was done in America and the work that was done in the former Soviet Union on inflation.
Yes.
Alan Guth and Andre Linde, who are great friends now, and both in the United States, but there was all sorts of just trouble getting papers out, work being done independently that wasn't known about.
Yep.
Getting scientists out of the Soviet Union as well to give talks at conferences. And I better go back and read the chapter. I have a chapter with a scientist, a Japanese physicist called Nobuyuki Sakai, who also talks about the fact that I think, he's of a younger generation and he had learnt about inflation from the papers of Alan Guth in the United States and Andre Linde, formerly of the Soviet Union. And he only found out afterwards that there was a Japanese scientist who had also sort of around that same time independently come up with similar ideas on inflation. And it was kind of funny to him that he hadn't heard about the work in his own country, but had known about it from abroad.
Yeah. I was going to say, I also think that there is a sense in which very few ideas are truly original. Everybody's thinking about similar things. If they're working in the same field, they're all thinking along similar lines. I had this mistake when I was young and stupid. I was convinced that I had these great ideas that were novel and no one had ever thought of these before. And it turns out that that's not true. People have thought of these things. Maybe in different ways. I may have had novel ways of thinking about them. And it also, some of it matters how you communicate that. So the quality of the papers you write. If you write a really, really dense, difficult to digest paper, or it gets published in an obscure journal, it may not get the attention that it deserves. There are papers like that that have been lost to time. I don't want to speculate on any motivation here. I just think it's just interesting that this came out.
Indeed.
I also want to emphasize to Hopfield and Hinton that I actually had them as number one before the plagiarism stuff came out. I put them at number one simply because it was a big story and it made a big deal in the physics community. Physics social media blew up. It cited a lot of opinions. And I want to emphasize, too, it's good work. It's important advances.
I'm going to take you back to the outrage.
Okay.
At the time on social media, because we discussed one sort of form of it, which was just, this isn't physics, this is computer science. It shouldn't be awarded as physics. And we've discussed that, and it feels like, this is just going to be a matter of taste.
Yep.
Some people are going to go, you know what, Hopfield networks, it's physics-ish. I'm fine with that. And some people are going to go, no, it's not. It's not really. It's, whatever else it is, it's not physics, whatever.
Yep.
But there seemed to be another sense in some of these comments. And I'm not, again, thinking about any one particular comment, but it came up a few times. It came up from different places. And it was almost a sense, not just of upset that this was, this was the wrong subject. And there are all sorts of things that happen with the Nobel Prizes where physicists and chemists and biologists are sort of winning each other's prizes. But it felt like there was some aspect of fear, some sense, and again with the chemistry Nobel Prize, going to DeepMind about what is science.
Yep.
And what is a scientist, and how is AI sort of exploding into people's lives and into labs and into what science actually is and how it is done. I got a sense that people were really very defensive and really very worried about that, and they felt like something is happening, something has changed. There's been a marked change in what we think of as being scientific progress.
Yes, and I think a lot of people worry, there's a lot of existential dread about AI in the world in general right now. And it doesn't help that the incoming administration in the United States has said they are going to take the regulations off AI completely, that they're just going to set it free. And I think there are people that are perhaps scared of that we could end up with something like Terminator or Blade Runner or something like that. One of the things that you have to do, and this is a touchy thing, but, is the discovery itself worthy of recognition outside of what its applications are? Normally, you'd be like, yeah, that, absolutely. Well, but if that discovery could lead to, I don't know, wiping out humanity, which I don't think is going to happen, but there are physicists who honestly believe that, by the way. There are legitimately physicists who are convinced that AI is going to wipe out humanity. So there's this concern that if we recognize this, or we recognize something that ultimately is, it's kind of like, here's a Nobel Prize for nuclear bombs, right? Which there was never a Nobel Prize for nuclear bombs, but there certainly were Nobel Prizes for things that contributed to nuclear bombs. Nuclear fission won a Nobel Prize. Should they have not won the Nobel Prize because it led to nuclear weapons? And by the way, they knew it at that time that it would lead to that. I mean, everyone knew. The moment that Meitner and Hahn achieved fission, everyone knew instantly nuclear weapon. So I think there's this concern there. I also think a lot of scientists are scared also from the fact that they feel like their own jobs are in danger because AI may be able to do it better. I personally don't think that is going to happen. I do worry about AI, but not in the same way everyone else worries about AI.
What is your worry?
All of this automated stuff is taking away humanity from us.
Yes. In the past, the idea of technology was to free us from mundane tasks so that we could enrich our lives and unleash our creativity. And now we seem to be outsourcing creativity to AI to give us more time to do grunt work and housework and mediocre and mundane tasks that don't really feel very fulfilling. It feels very regressive in that sense.
AI is supposed to do my laundry, not write my novels. I don't think AI is going to be as transformative as people expect, or in the ways that people expect it to be transformative.
One of these days, we're going to end one of these lists on a happy note.
Yeah, right.
Instead of doom and gloom, which always seems to happen. But congratulations to Geoffrey Hinton and John Hopfield for winning the Nobel Prize in physics. Fingers crossed it all ends well. And we'll be back next year for another podcast rather than having been replaced by AIs who will just come up with a list of the top 5 results.
Indeed.
Of 2025.
And I just, one more shout out, my late friend Carl Gertman, who was a big fan, and Carl will sorely be missed. And I've known him for many, many years. And in addition to knowing him through my local astronomy club, he was also a longtime judge for Odyssey of the Mind, which is my kids used to do when they were in school, which is it's a great program. So
rest in peace, Carl.
Rest in peace, Carl.
I want to work the word controversy into that, but I can't. So I shall leave it. I shall leave it at that.
Leave it there, yeah.
Big congratulations to everyone that got onto the list, and also to the runners-up who didn't quite make it. But this year we didn't have any dishonourable mentions. So, congratulations to everyone. You should all be proud of yourself. On the podcast page, qspace.fqxi.org/podcasts, you will find links to more information about pretty much everything. The news articles we've been reading, the original papers, some images where relevant, and some tweets where appropriate. And I will say, Ian, thank you very much for your list. Please be careful in the coming year to not get struck by lightning. I will, yes. And thank you, Zia, for making this possible and doing all the hard work of the editing. Oh, thank you, Ian. I appreciate that. So, thank you again for listening. You can follow us at FQXI or at FQXI Physics, pretty much everywhere. And email us at podcast@fqxi.org and visit QSpace to subscribe to FQXI's newsletter and learn more about the research that FQXI funds. Happy New Year from all of us at FQXI. I've been Zia Morali.